All right, let's go ahead and get started. In this video, we're going to be looking at trends of the periodic table. Now, we've previously seen that Mendeleev arranged elements according to atomic mass, and in doing so, placed elements or arranged elements that had similar physical and chemical characteristics together. Moseley later refined this process by arranging them according to atomic number. But if we look, for example, to elements on the left side of the periodic table, all of these tend to be metallic. Everything to the left of the zigzag line is metallic, has luster, malleable, ductile, conducts heat and electricity, all the characteristics of metals. If we look on the right side of the zigzag line, those are non-metallics, the absolute opposite qualities. They are brittle, they do not conduct electricity, and so forth. If you look at this column right here, this column, when placed in order, when these elements are placed in order of atomic number, this column, called the alkali metals, are extremely reactive. In fact, as you move down the column from lithium to sodium to potassium and so forth, the reactivity increases to explosive reactivity of francium with water. On the other side of the periodic table, we see the exact opposite. Helium, neon, argon, and so forth, absolutely non-reactive. Why? Because they have an octet. They don't want, we now know, Mendeleev did not know, certainly Moseley didn't know, but we now know that they have a full octet and therefore are very unreactive. The point is that these are some very generalized rules about the periodic table, but what we want to do now is we want to focus on some more subtle trends of the periodic table. Let's start with atomic radius. Well, what do we mean by atomic radius? Well, as it turns out, the atomic radius is the distance from the nucleus of an atom. Let's draw 3 protons. We'll make this one lithium. And we want to take a look then at the distance between the nucleus and the outermost electron. So if I put an electron there, an electron there, I'll circle those, and I'll put one more electron right there. The distance between the nucleus and the outermost electron we call the atomic radius. And as it turns out, the atomic radius size is going to increase as I move from upper right to lower left. So the largest atom on the periodic table would be francium, and the smallest would be on the upper right-hand corner, helium, right? Helium. So that is the trend for atomic radius size. Now we're going to answer a couple of questions regarding size. The first one is this: why do atoms decrease in size as you move from left to right across the periodic table? So let's picture a particular period, let's say the second main energy level, and answer this question. And here's what it says. As the atomic number increases, the pull on the peripheral electrons increases since there are more protons to rein them in. Okay? That's an increase in nuclear charge. So let's take a look again at a particular row. Let's take a look at this second row, going from lithium to beryllium to boron and so forth. Notice that the electrons are all going to be placed in the same main energy level, which is the second main energy level, right? So as I go from lithium to beryllium and so forth, what I'm going to see is I'm going to see electrons being placed in the same main energy level. So if we were to draw that, we might draw a nucleus like this, right? And we'll start with 3 protons just like that. And then electrons in the periphery, we'll start with 2 here. There's 1 electron there. There's 1 electron there. We'll put a third electron a little bit further out. But from this point on, every time we add a proton, we're adding an electron, but not further out, but rather in the same main energy level, right? So if I add protons, I add electrons. So what's going to happen is that these protons are going to have more pulling power, what we call atomic or nuclear charge. They're going to pull these electrons in the periphery closer in and thus reduce the size of the atom. So that's the explanation for why the atomic radius size gets smaller as you move from left to right. Now let's answer another question. Let's take a look at this one. Why do atoms increase in size as you move down a family or group? There are two important answers to this question. The first is that the electrons are being placed into higher energy levels. So, for example, if we go to the periodic table again and we look at this group here, we're going to go from lithium, say, to sodium to potassium. What we see is we're going from main energy level 2 to 3, 3 to 4, and so forth. So as I go from lithium to sodium to potassium, I'm not in the same main energy level. I'm moving into progressively higher main energy levels. I'm placing electrons into progressively higher main energy levels, and therefore it stands to reason then that the atom would get bigger and bigger and bigger. So unlike what I saw in the previous question, if I'm starting, say for example, again with sodium, so I'm going to start with sodium, just like this, 1, 2, 3 protons in the nucleus, and then I'll start drawing electrons. I'm going to put 2 here, 1 there, 1 there, and 1 there. But from this point on, let me circle those. From this point on, when I put electrons in, I'm putting them in to higher and higher and higher main energy levels. Therefore, those electrons are going to be farther away from the nucleus. The distance from here to here is going to increase just by virtue of the fact that they're farther away at higher energy levels. So that's one reason that atoms get bigger as you move down a period or a group. But there's another reason, and the second reason is something called shielding. Let's explore this concept. That is that if I look at an electron in the outer part of the periphery, I'm going to outline this one right here as the one that I'm interested in. This electron right here in the very outer part is being pulled towards the center of the nucleus by the nuclear charge. However, the intervening electrons, these electrons here, are mitigating or are lessening the effect of the attractive force, allowing that electron to kind of drift further out, and in doing so, make the atom bigger. So two reasons why the atom gets bigger as you move down a period or a group. Okay? Hope that makes sense. Now, let's take a look at another question. In fact, let's drop down to number 4. And what we want to do is we want to define electronegativity first. So what is electronegativity? It is the tendency of an atom to attract nearby electrons. The tendency of an atom to attract nearby electrons. So, let's take a look at an example. Let's take, for example, one that we're familiar with, and that is water. All right? So, we know that water is made of hydrogen and oxygen, just like that. And between the hydrogen and the oxygen are electrons or pairs of electrons, just like that. As it turns out, oxygen wants to hold on to those electrons more than hydrogen. It is more what we call electronegative. And so the electrons tend to be pulled toward the oxygen and away from the hydrogen, okay? Toward the oxygen and away from the hydrogen. That's called electronegativity. Now let's answer question number 3. Why don't noble gases, why do they not have electronegativity? Well, as it turns out, noble gases already have the full octet. They don't want electrons. So when we talk about the trend that we're going to talk about right now, we're going to exclude the noble gases because they don't have an electronegativity. But here's the trend. The trend is that as you move from lower left to upper right, electronegativity, otherwise known to us as electron affinity, increases. So electronegativity or electron affinity increases as you move from lower left to upper right. Exclude the noble gases from this category. They don't want another electron. All right? Now we have one last trend to discuss, and that is first ionization energy. So now we've done electronegativity or electron affinity. Now we want to do first ionization energy. The trend here is lower left to upper right. It increases, right? Lower left to upper right, it increases. But what is it? What is first ionization energy? Well, it's the force required to remove an electron. So, how does that work? Well, let's take lithium's my favorite atom. So I'll use lithium. So lithium, 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 okay? So lithium, 3 protons just like that, and so we're going to have 3 electrons. I'm going to put 1 electron here, 1 electron here, and 1 a bit further in the second main energy level. The first ionization energy is the energy that would be required to remove the last electron, just like that. Just to take it off is going to require energy, right? Because these protons are not going to let you do it for nothing. They're going to offer resistance, but you can get that last electron off and make an ion. You're going to have an Li plus 1 ion because you're going to have one more proton than electron. So to remove that first electron is called the first ionization energy, right? The first ionization energy, and we now understand that and know that trend, right? All right, so now let's continue. So what we want to do now is we want to ask the question, what is happening at atomic radius size as we move from left to right? Well, this is lithium. In this row or this period, as we move from left to right, the atomic radius size decreases. We've seen that. Then it increases again at sodium and decreases again. This is called periodicity. So as you move from left to right, it increases. The atomic radius size increases, right? Increases. Now let's take a look at ionization energy, just the opposite. As you move from left to right, say from lithium to neon, ionization energy, with a few exceptions, is going to increase as well. It's going to increase as well. So now that we've done that, let's compare atomic radius size. On the left side of the periodic table, atoms are going to tend to lose electrons. Lithium becomes lithium plus, sodium becomes sodium plus, and so forth. That happens in the second and third column as well. And atoms get smaller when they lose electrons, and we see that there. And then let's go to the other side of the periodic table. The atomic ionic radius size increases because I'm adding electrons to atoms for them to become anions on the right side of the periodic table. So on the right side of the periodic table, ions are bigger than the atoms from which they came. On the left side, they are smaller. Folks, I will see you on the next video. Have a good day. Bye-bye.